So welcome once again, everyone, and let's get started with the news. On Thursday of this week, there was an annular eclipse of the sun. It was not visible from Southeast Florida, but there were places on the internet where you could see videos and pictures that were posted from where they could see it. Follow the links that I sent in the email and you can see some pictures of it. The Juno spacecraft, which has been in orbit around Jupiter, actually changed its orbit and did a flyby of Jupiter's largest moon, Ganymede. By the way, there's a total of 79 moons around Jupiter. And this is the first close-up video of Ganymede in 2 decades. Last time was when the Galileo probe was in orbit around Jupiter. Now, being a moon with very little atmosphere, it looked somewhat moon-like. There was lots of craters. In addition to NASA's Veritas and Da Vinci Plus probes, the ESA will be sending its Envision orbiter to Venus in the early 2030s. So in the radio telescope realm, the CHIME radio telescope in Canada has, from 2018 to 2019, recorded 535 fast radio bursts, which we don't quite fully understand where they're coming from as far as physics events. We don't quite understand where they're coming from a physics perspective. They presented them this week at the American Astronomy Society meeting. If you read about, they've discovered 535 fast radio bursts this week. No, they discovered them back in 2018 and 2019. They're just presenting a report on them this week at the AAS meeting. So the Ingenuity helicopter on Mars has flown successfully again. So now it's the little foible that it had the last time it tried to fly. They figured out how to deal with that, and it successfully flew. So I guess Ingenuity is going to be parked on the side for a little while Perseverance actually gets started doing its own rover science thing. We'll get back to Ingenuity later at some point. China's rover on Mars is, I guess, feeling left out in the popularity circles. It's starting to take pictures, and even took a selfie of itself. I wonder where it got the idea how to do that. But it took pictures of its lander. It took pictures of itself. Don't know what science it's doing yet. And they've discovered what is referred to as the giant arc of galaxies. They found a series of galaxies that are stretched across an area many times the diameter of the full moon, as far as when you're looking up at it in the sky. And the significance of this is not that galaxy clusters don't exist. It's the fact that this is viewed as a large string of galaxies, which would be in violation of the cosmological principle that matter is spread homogeneously across known space. Sure, you can have galaxy clusters, but you shouldn't have something this large that has a string of galaxies in it. Maybe it's new science. We will find out. As they do more observing, they may find more of these. And then thanks to Joanne, I picked up a couple of more items here. I don't always post news items as new when I don't think they're new. And like I did with the CHIME radio telescope observation state, well, these were actually back in 2018 and 19. Well, National Geographic has finally admitted to there being a fifth ocean, the Southern Ocean around Antarctica. USGS has, reports back as far as the mid-1970s where the Southern Ocean is mentioned. There is a current that flows around the continent of Antarctica that actually distributes temperature evenly across the southern half of the globe. So that current is recognized as an ocean and has been that way for some time. I guess that National Geographic was falling a little short on its revenue goals. And if we suddenly put a label of Southern Ocean in all of our maps and books, everybody might want to buy new ones, new and updated ones. They found a large dinosaur fossil in Australia. It is similar to the ones that they found in South America a few years ago. But if you didn't read the fine print, you would think they found the largest dinosaur ever. Yes, they found the largest dinosaur ever in Australia. So that's why I didn't put that one out there. But I did find one shortly before the session, technology called space plate. It is nonlinear optics based upon nanomaterials. This is creating pathways for light to follow that are down at the billionths of a meter size. And apparently by making these channels for light to follow, they can have the same effect as the focal length of a telescope. If you think about a telescope, magnification is not derived based upon the diameter of the telescope. That's image resolution in detail. The actual magnification is you divide the focal length of the telescope by the focal length of the eyepiece, and that gives you the X magnification. So if you have a very long focal length telescope, and you can fold it with mirrors, but the longer the focal length for the same focal length eyepiece, the more the magnification. But now using nanomaterials, they can make a telescope that would be paper thin and still give you the equivalency of a long focal length telescope. That will be interesting to see if they can commercially bring that to light, because that would be a huge shift in telescope design for amateurs. So we'll see, just put a push pin in that and think about space plate nanomaterials and nonlinear optics to make telescopes paper thin. It'll be interesting. So any other news items that I've missed?
Monroe,
Yes.
the Vulcan person put something in the chat. The chat? I can't pronounce that name.
That's the giant dinosaur that they found in Argentina. So that's the name of the dinosaur they found in South America.
Are they trying to say that's the largest one?
No, neither one is the largest one. They're both about the same size.
Oh, okay.
So the one that they have in South America and the one that they have in Australia are roughly the same size. But those two are the biggest ones that they found.
That was just one bone, right?
The one in Australia is one bone. I think they have more than one bone in South America. Depending
So there's
upon
a bigger dinosaur, but we don't have a bone of it?
No, we have the one in Australia, we have a bone of it. We do not have a full fossil.
Right.
So it's kind of like saying, how tall is that person? I don't know. We can scale them based upon the length of their femur. As more information comes to light, they'll clarify things, but it's a matter of largest found in Australia versus largest ever found, because the one in South America is similar size. So tonight we're going to be talking about astronomical observing in a particular kind of light, a particular source of light called Cherenkov radiation. So we're not talking about observing in radio or infrared or wideband or human visual light or X-rays. we're going to focus on how you indirectly observe cosmic rays. So cosmic rays don't make it all the way down through the Earth's atmosphere. The atmosphere kind of stops it, but it doesn't really stop it, it transitions it. So the cosmic rays transition to high energy electrons called muons in the mesosphere, the upper atmosphere of the Earth's atmosphere. What is captured at the ground is the interaction of cosmic radiation in the upper atmosphere, producing muons, which make it down through the atmosphere, where they interact with a variety of materials and they produce different wavelengths of light. So we'll discuss muons as they transition through materials, which produces Cherenkov radiation. So what is that? Cherenkov radiation is a particular kind of light produced when essentially light slows down. And it slows down going through a non-conducting medium like water. So if you've ever seen the images of a core of a fission reactor, which is the picture you see here, as the radiation comes out of the core, it basically slams into the water and moves more slowly. And if you're going to do that, you have to give up energy. And what it does is it produces a particular kind of light. You will see descriptions of how this is analogous to a sonic boom. Well, kind of, because the aircraft does push against the air, which results in the transition and you get a boom. But the aircraft actually goes faster after the transition. So it's going below the speed of sound. And at the point where it transitions the speed of sound, it's where you get the boom. So the aircraft goes faster. In this case, the radiation would like to be traveling at the speed of light, and it encounters a denser material like water, and it slows down. But to slow down, it has to give up some energy, and the energy is the photons that you see. We'll get into the detail as to why it's this unusual palish green glow, mostly blue, but it's got some green to it, as you can see. First time I ever saw it was in the James Bond movie Dr. No, where they were both wrestling in the core of the reactor, which is facetious because they would be cooked by the radiation of the heat. But they made the glow of the reactor white because it worked better on film, I guess. And they injected air bubbles to make it look more hazardous. Anyway. So when the beta particles with high energy electrons, muons, are emitted by the fission reaction, they slow down when they go through the dielectric, the non-conducting reactor coolant water, to about 0.75 of C, causing them to emit this radiation. Some of it is in UV, which is invisible to us. Some of the wavelengths are stopped by the water. So what we end up seeing is this pale blue-green glow. So as gamma radiation from cosmic particles coming from other places beyond the Earth, the sun, or things beyond our solar system that are high energy, they react with atoms in the upper atmosphere. They produce muons. These interact with materials that produce Cherenkov radiation. And the radiation is solicited to be produced by either water in the atmosphere or by giant tanks of purified water. So Cherenkov radiation was not named after Marie Curie, but it was first documented as being observed by her in 1910. Pavel Cherenkov, that's the Russian spelling of it, actually documented it in 1934, for which he won or shared the 1960 Nobel Prize in Physics. And there's a couple of links there to more information. Whenever I have links in the presentation, I always put them as text in the comments once the video is posted on YouTube. So you don't have to type them in, you can just click on them. So here's an actual spectra of Cherenkov radiation. And I took this from a thesis on doing this using tokamaks, sort of artificially created Cherenkov radiation, but the spectra is the same. And you can see that that central vertical dotted line is the highest energy peak, and it's kind of purplish, but that doesn't make it through the water, and the ultraviolet isn't visible by our eyes, but our eyes are very sensitive to green at around 555 nanometers. So we get some of the blue and some of the green, so it comes out as bluish green. So if the detector that picks up the radiation is in water, you get this bluish green sensitive range, and you want to build your detectors to match that. If you're picking it up through atmospheric water, then you probably want to shift it up closer to 420 nanometers. So if you want to do science with Cherenkov radiation, you have to decide, do you want to detect it and count the occurrences of it, or do you want to try and do imaging with it? And that is two different kinds of instruments. If you just want to detect, you don't need to focus the radiation. You can just hang out detectors in giant vats of water, and you can detect when it occurs. If you want to do imaging, then you first want to concentrate or focus the radiation. So you would use something that looks like a telescope or reflector telescope to do this, and then you would have your detector pick it up. One of the oldest types of detectors for light in astronomy is something called a photomultiplier tube. Yes, it's tubes, folks. And you can detect Cherenkov radiation with a special kind of photomultiplier tube, although they are starting to work with solid state materials to pick up the radiation that way. And in either case, they use very fast analog to digital converters, and we'll get to the specifics of how fast they need to be. So there's two types of instruments you'll see: shielded water pools, where they just want to detect and count, and then matrices of instruments where they want to try and image. So far they haven't really imaged much. They've done some detection and direction. So what kind of observatories would these be? It's not the kind of observatory where you're going to go put your eyeball up to an eyepiece and see Cherenkov radiation. It doesn't work that way. It's too short-lived and too bursty and not that predictable. So you're not going to walk, it's not like looking at a planet where you can, if the planet's visible above the horizon, you can always pop your eye up to the eyepiece and take a look at it. Cherenkov radiation is too short-lived and too bursty for that. So you have to dedicate instruments to do this. And you can either dedicate large pools of water or detectors. If you dedicate large pools of water, you're not going to be moving those around the sky. Basically, they weigh hundreds of pounds to thousands of pounds. And so you plop them down in locations, and then you let the Earth rotate, and that's how you scan the sky. So the amount of sky you see is limited, and the exposure duration is also limited. So you want really fast detectors. So the water detectors are trying to determine, did it occur? And if it did occur, if you have enough of these tanks, then you can determine what direction it occurred. And then if you can send out the signal fast enough, maybe then you can have other telescopes take a look at it in other wavelengths. If you're imaging, then you want to be able to steer your imaging instrument so that you can point it at a specific thing and say, is there any Cherenkov radiation coming from that direction? And you can either use photomultiplier tubes, which are low resolution, or you can use cryogenically cooled low noise amplifiers with solid state instruments. If you're familiar with optical telescope imaging and you've ever encountered a Schmidt telescope or a Schmidt camera, where the secondary mirror would be of a reflector, that's where you put the camera. Well, in this case, that's where you put the detector. But they don't call them Schmidt cameras. There's a different name for them. We'll get to that. Sometimes they'll put together multiple of these imaging detectors as a small array to try and create interferometry arrays out of them. The largest one is the Cherenkov telescope array that is going to be deploying multiple detector imagers at 2 different places on Earth and try and do large telescope imaging with them. So far, they've demonstrated practical designs of both of these techniques, so they can say they're detecting things, but they haven't fully deployed everything that they're planning on deploying. So one of these bursts lasts from 5 to 20 nanoseconds, which is billionths of a second. So if you want to detect them, you can use your water detectors to cover very large areas. But if you're not pointing at it, if you're letting the Earth rotation pick it up, you need a large detector, a large dense area of detectors, or you need to have fewer detectors over a much larger area. So what it does is it actually picks up the Cherenkov blue-green fluorescence emissions in the water. They use very fast analog to digital converters to pick up these very short-lived bursts, but they have to be sampling continuously because they don't know exactly when they're going to occur. When they first started doing these, they had a single photomultiplier tube, and they would put a fisheye set of lenses so they could see the light in any direction. That was just to confirm that they could detect them. But now that they can detect them, they've kind of ditched the fisheyes and just put in a lot more detectors. In the case of the imaging, it would be disappointing. The imaging is not megapixel resolution, it's hundreds of pixels resolution. You can only make a photomultiplier tube so small, so they have a little under 500 pixels worth. But as they start to use solid state detectors, they can get up to a couple of kilobits or kilopixels worth of detectors. So we're not at the megapixel yet. Okay, has anybody ever seen these alongside the road? These sort of white, large, round tanks that you probably go, oh, that's just water for the cattle out in that field. It might be, or it might actually be a Cherenkov radiation detector. And there's a couple of kinds. You can see the top picture. This one's in Mexico. They have a dense population, a couple of hundred detectors packed very closely together. And then other types are like in Argentina, where they have a lot more detectors covering 10,370 square kilometers, so a lot of detectors, but they're pretty much all looking like these plastic water tanks. In China, they want to go one bigger. They made the water containers enormous underground containers, and they just let the top of the detector array stick out. So you won't even see much above ground except these little white squares of polyethylene plastic. But they cover 360 acres, and they're not done yet. They're still building this thing out. So that's the detector type. They're not imaging rookies. They're just trying to detect. So before I get to the imagers, any questions? Comments? Okay, now we get into the imager types. Okay, so I have a couple of slides here on the imaging types. They all look pretty much the same. They're these open frame, no observatory dome looking reflector telescopes. They have a Cassegrain hole in the center of the mirror, but that's not what it's for. That's not where the light goes. The light actually winds up in that box hanging way out on the end. And you might find a couple of these types of telescopes at a particular location. They might all be the same size, or there might be different sizes. The one that's in the Canary Islands is kind of interesting. You can adjust the curvature of the telescope so that you can focus it. And until we get imaging of it, it's not quite clear as to what the shape of the reflector should actually be. How tightly focused should it be? So that's why you have some that are adjustable just to make sure that all of the light is focused on the detector, and you have others that are attempting to actually focus the light to see what they can see. The one in the lower right is the focusing mechanism, which uses laser beams. So that's why you see all the red lights. Here's another couple of types. The Cherenkov telescope array is the, I guess you could say, the most ambitious. They want to build a lot of these types of telescopes of different sizes that operate at different wavelengths. And then you have the highest one, which is in India. It's at 14,800 feet. This telescope is so high, you have to be on oxygen to be up there to assemble it and work with it. So they actually operate it remotely. There's nobody at the site. So they actually get a lot of clear day, but you'll notice that the picture that was taken actually has clouds overhead. So these are all sensitive to, well, we can't really pick up the radiation if it has to go through clouds. We can't compete with sunlight, so it's showing it, doing it during the daytime there, which is not good because the sun puts out a lot of its own radiation. Don't want to be confused by that. You can't do it if the moon is more than half full, because it also produces light in the particular wavelengths. Not that it's Cherenkov radiation, it's broad spectrum radiation from reflected from the sunlight. So it is noise. So I wanted to pick one of these telescopes apart and look at the details of them. So I picked one of the Veritas imaging style Cherenkov radiation telescopes in Arizona. They have 4 of these at this site. They're separated by about 330 feet each. The first light occurred in 2005, February. They're 39 feet in diameter, the individual telescopes, because you may not know in advance what you need to look at. They slew very fast. They can slew that giant telescope at 1 degree per second, and has a mechanical positioning accuracy of 0.01 degrees. So it has to have a huge mass on the back of it, and you can see that. Let me see if this works. There we go. You can see the huge mass back here to counteract the weight of the imager. You can also see all the individual mirror cells that make up the reflector, and how you can curve them. They're under motor control. You can curve them so it looks a lot more like a nice, smooth, reflective surface, but they're individually aligned to focus on the detector. This is the detector. It's only a few millimeters in size, and this is a custom designed reflector, kind of like a honeycomb, to get all of the light focused down into it. Here's one individual detector. That's the photomultiplier tube. It's about as big around as the end of your little finger, and they have two connections, power and ground, and it produces, does amplification. There's a little circuit board inside there that, in addition to the photomultiplier tube, it also does its own low noise amplification. And for those people not familiar with the photomultiplier tube, this is a diagram of the innards of one. It's a vacuum tube. It lets the energy come in. It hits a cathode, which is a coated piece of metal that will make it produce photons. The photons then go through a staged series of amplifiers. These are kind of like radio tube amplifiers, and that's what produces your final connection of your anode out to produce signal. So they have 499, not 500, 499. Why they didn't go for the extra one, but they use off-the-shelf Hamamatsu photomultiplier tubes. If they could get them smaller, they would, but they want to also make them sensitive. So that honeycomb reflector array is called a Winston concentrator. I guess named after the guy that came up with the concept to do it. They can detect UV and visible through almost near infrared. Pixel spacing is 0.15 degrees, which is enormous compared to optical instruments that are at micron level pixel sizes. The field of view is 3.5 degrees, so you've got to point it at your target in order to get the image. And since the bursts are unexpected, short duration, 4 nanoseconds, you've got to stare at something for a long time to get enough radiation detected. Remember, this is very high energy. So the photons that they're picking up have 100 giga electron volts to 10 tera electron volts. If you want a comparison, visible light is only 1.6 to 3.4 electron volts. And these are billions of electron volts to trillions of electron volts. So very high energy. They sample these at 500 million samples per second in order to get the Nyquist theorem of, you got to sample at twice what you want to pick up. So 2 nanoseconds is what they want. So they're sampling at 500 million samples per second, which sounds inverted to me. They're only 8 bits. It's not like they're doing 12-bit or 16-bit analog to digital conversion. So it's literally the values are 1 of 256. Not a lot of range. But because there might be data communication delays on the data getting from the telescope to the control center, they buffer a whopping 64 microseconds worth of those 2 nanosecond samples. Like I said, they need a clear, dark sky. They can't have rain or clouds. The moon must be less than 60% illuminated. This was also interesting. They want some humidity so that you can get your Cherenkov radiation, but not too much humidity because then it'll be too scattered. So the humidity must be less than 50%. And the telescope doesn't want a lot of gusty wind wiggling it around. So any gusts have to be less than 50 kilometers per hour, which sounds like a lot. So they use multiple of these to distinguish which direction things are coming from. And then they use multiple detections to identify, is that really noise or is that really Cherenkov radiation from the direction we want to see? Strangely enough, in order to monitor their alignment and weather, each one of the telescopes has a CCD camera attached to it to just get a visual image of things. Are we pointing in the right direction? Are there clouds forming? So every 2 seconds, they'll take a imaging snap of that. And sorry, since they haven't figured out quite the focusing yet, no pretty pictures, but I do have in the lower right there a map of data that they've gathered and the intensity of it. And this is just by the Veritas detectors. So any questions about,
Yes, I might have missed something at the beginning.
okay.
Why are all these people searching for this? What's the significance?
Oh, we're trying to detect indirectly gamma radiation. So we have telescopes that we've sent up into orbit that will detect gamma and X-ray radiation. But if you want to study a bunch of things, having just one gamma radiation telescope is kind of not enough, because gamma radiation, as you can see from this, is very directional. So if you want to study one star and its gamma radiation, and you've sent up one spacecraft, you can look at one thing at a time. So by having all of these, you can look at multiple things based upon which direction the Earth is facing at the time. But since gamma radiation doesn't make it all the way down to the ground, you have to look for the indirect gamma radiation sources. So that's what the Cherenkov radiation turns out to be.
Right. Gotcha. Thank you.
Okay. So what can we look forward to in astronomy through Cherenkov radiation? Where things are coming from. So if you have a bunch of these water tank detectors and you know which way the Earth is pointing at the time, you can tell what direction things are in. But remember, unless you have a fine sense of where it's coming from, using the imaging detector really isn't going to do you much good. So you use the big water tanks to tell you it's that direction. And then you can use the multiple imaging detectors to detect where it really is. You know, it's that star or it's that galaxy. And then you'll figure out if the burst is lasting long enough, you'll figure out how to get all the mirrors pointed right to get the right amount of focus to actually see something. So we haven't really imaged yet. We have imaged in gamma radiation. There is a gamma radiation telescope in space. It's one of these Lagrange point things that's trailing behind the Earth, so it's kind of in the shadow to keep down the noise. And we have imaged. Think about it this way. If you're really imaging in gamma, what do you use to focus it? Well, if it's optical, obviously you can have mirrors. If it's radio, you can have, you know, mesh dishes or solid dishes. But if it's gamma, you're not going to really put out enough energy to change the direction of the gamma radiation. It just comes down the tube, and you have very dense metal plates around it to absorb any stray radiation, but it's just straight down the tube and you image it. So that's why you don't see a lot of gamma radiation images. You do an X-ray, because in X-ray we can have magnetic fields that will steer the X-rays and focus them. So X-ray, we do have X-ray telescopes that can focus images somewhat. Just like when you get an X-ray or a CT scan, they can focus the X-ray beam. So where I got interested in this and the Cherenkov telescope array is they were trying to create an array of hybrid detectors, big, small telescopes at different wavelengths, and how to create images through post-processing. So that's where I started to go, okay, I know CTA is looking for Cherenkov, but they're going to write some software that's going to be open. And we'll have access to that software and we can use it for radio. So how come I've never heard of these things before? Well, they're at very high altitude in rural areas to avoid interference. And if you were driving along the road and you saw these things, they would just like look like giant plastic water tanks. And if they're widely dispersed, you just go, well, that's water for the cattle in the field. Nope, it's a water tank detector of Cherenkov radiation. And it's going to get even harder to detect them as they're starting to bury them in the ground to reduce even more interference. And the only thing that's exposed is the plastic top of the tank. If you were to go to an astronomical observatory at high altitude and you see one of these instruments, it would just look like a reflector telescope with no dome around it. And you go, oh, that's an interesting design. There have actually been media releases announcing, you know, first light, and we're building this, and we just installed that. So if you weren't looking for it, you wouldn't see the announcement. Unlike other people, I'm on the email list for these kinds of announcements. So, oh look, here's the monthly CTA report of, how they're building out their telescope. They've actually, over the course, worldwide, they've spent billions of dollars building and staffing and operating these sorts of instruments. It's just another way of looking at things in the sky. And after all, they don't need our approval to go off and do these things. We elect officials to commit funds to go do these projects, and they just go off and do it. So in the US, the National Science Foundation allocates funding to do these kinds of things in the US, and different universities pick up on it, and different existing observatories pick up on it. And, our individual people's awareness of these things is optional. They're obviously hiding in plain sight. If you don't know what you're looking at, you won't know what you're looking at. They're not top secret. Besides that, I'm a polymath, and if you don't stop me from learning about these things, I learn about them. Much like we learned about, relativity, and then it started showing up in things like your MRI technology to get your body scanned. Cherenkov radiation, or Cherenkov luminescence imaging, is something that's now being used for tumor detection. So when you go to get your PET or your CT scan, they give you this antimatter, positronic radionucleotides. They give you antimatter, and the antimatter settles in certain parts of your body that they can detect it. And as you can see here, the graph on the left, one of the places it settles in to a very high degree is large tumors in your body. So it settles in other organs to a much lower degree, but in tumors, small tumors or large tumors, it actually forms luminescence that you can detect, pick up with these scanners. So here's some bodies of some mice that have been given it. And you can see that after a certain number of hours of having this agent in their body, it detects the tumors at different levels. And depending upon what type of material they inject them with, it will show up differently.
It's
So,
injections. They don't drink it.
no, it's injections.
Okay.
The one that you drink most often is barium.
Yeah.
The one that is positronic, that's typically injected, and they'll say something like, "Now you're going to feel warm. You're going to feel a warming sensation." That's the fact that this material they're injecting in your body is going to start interacting with your body and producing lots of energy. So you'll feel the warmth of it. So that's how something we want to do in astronomy with new fancy kinds of instruments turns out to actually be useful in medicine in detecting tumors. So, any questions? Comments?
There must be a lot of people who care about this. I never seem to notice this. I didn't think to care about gamma rays.
Well, there's been a lot of investigation into detection of them through Cherenkov radiation, but also the use of them. If you've ever heard of something called the gamma knife, that is used for blasting tumors. So we've been, studying more about high energy physics. And, if you're looking at UV, that's a certain level of energy. Then you can move up to X-ray, that's a certain level of energy. And then you get up to gamma, which is, as they refer to it, exotic levels of energy, very, very high levels of energy. But
Where are you saying the gamma rays are coming from?
Well, the gamma rays are coming from exotic matter in stars and in galaxies. So the Crab Nebula, for example, puts out a lot of gamma radiation as a pulsar. Pulsar is a neutron star or a fast spinning black hole. And they put out a lot of radiation out their poles. And if they're spinning where they can face towards us, then you get a pulsar effect. So one of the ways that they've tested the Cherenkov imaging detectors is by pointing it at the Crab Nebula and seeing over time, as the pulse keeps hitting us, how much of the not directly gamma radiation, but indirect Cherenkov radiation they can pick up and detect. And then they use that as a judgment scale to say, okay, let's point at something else. We know how much radiation is coming out of the Crab Nebula. If we point to another pulsar, and over the same period of time that we get more signal out of it, we can judge how much more energy is being put out by that decaying star.
You see the chat?
The chat. Collisions of black holes, neutron stars, and what's the WD? So not next week, but in 2 weeks, we'll be discussing LIGO, where we'll actually discuss how gravity waves are detected. That's probably something people have heard about, but the most interesting thing is the latest generation of detectors. So if you look at the first photocopier machine or the first microwave oven, they were huge and expensive. And nowadays, photocopiers are just scanners built into your printer. And microwave ovens are, something that's, just big enough to do your popcorn. It costs under $50 at Target. So as technology is advanced, things are improved, they get smaller and cheaper. Who knew that LIGO, which is miles long in 2 directions, and they have multiple detectors over the Earth, who knew that someday that kind of detector might be as small as a wristwatch? So,
wow, okay.
You're going to want to watch that one in 2 weeks. But that will be measuring gravity waves and how the next generation of gravity wave detectors are going to be very fascinating.
They kept on rebuilding them and improving on them, these 11-mile long tunnels.
Yes. But that wasn't the most interesting part to me. The most interesting part to me was not that they're shrinking the detectors, but that it proves something that I've known for a while about light, which is when they increased the power output of the lasers that they use, it moves the mirrors. So they had a certain power of laser that they were using to bounce off the mirrors for the interferometry, the Michelson interferometry array. They doubled the laser output. And when they did, and they turned them on, they said, oh, look, gravity waves. And then the gravity waves lasted a while and then eventually died down. And went, what's causing that to happen? Well, it's got to be that the length from where the beam splitter is to the mirror has changed by micromillimeters. And what it turned out to be is the laser and the high density, the high flux photons hitting the mirror actually made the mirror swing at the microscopic level. So the concept of, do photons in a vacuum transfer momentum to heavy things? The answer became a resounding yes. We have to take this into account. So whenever they turn the lasers on, they have to wait for the bounce of the laser on the mirror to dampen down before they start considering that they've detected anything. And I just found that fascinating. But when they discovered that, they said, we've got some other things that we've detected that turned out to be false detections. If you've ever listened to rain on a metal roof, the rain, when it's falling steadily, even though the wind doesn't change, occasionally the rain will sound like it's going a little faster or hitting a little harder. That's because the density of the raindrops per square area varies with the clouds. So when the cloud has like a pocket of denser water, you'll get a slightly heavier, denser amount of raindrops on the metal. So you'll hear the change in numbers of drops hitting the metal and how hard they're hitting the metal. The same thing is true of a laser beam. When a laser is fired for a continuous period of time, the number of photons coming out of it at any particular point in time varies at a very small level. So the amount of photons kind of flooding and impinging upon the mirror and then reflecting back was changing. And this flood differential started to detect gravity waves, but it was a false
but
detection.
that doesn't change the wavelengths.
No, it doesn't change the wavelength. It changes the density of photons that are coming back. And if you have that different between one beam and the other, the interferometer will detect it as a gravity wave. So when you split the beam, some of the radiation goes down one tunnel, the other radiation goes down the other tunnel, and if it's not evenly split as to the flux, as to the density of photons, then one mirror will have more photons coming back than the other, and that causes a change in the interferometer, and you might think you've detected gravity waves when you haven't. So they had to actually monitor the energy output, at a very high rate coming out of the laser, and when they get one of these sort of sudden bursts of photons, they have to say, nope, discount that, not that, not that. And then when the laser stabilizes again, now you can start believing you might detect. So the duty cycle of the detector is now not continuous, it's variable. Sometimes they can say, we can detect now. Other times they say, well, not for these 5 milliseconds, we can't detect until the beam energy stabilizes itself again.